Assalamualaikum and good day. My name is Ainin Binti Ruzeman and I am currently conducting a research on machine learning based method for ground subsidence risk prediction around water pipelines in underground utility mapping under the supervision of Dr. Mimi Diana Ghazali. Ground subsidence is a critical geohazard characterized by the abrupt vertical collapse of the surface. In urban areas like Perlis, this is frequently triggered by damaged water and sewerage pipelines. When water pipelines leak, they wash away soil particles, creating empty subsurface cavities that eventually lead to catastrophic failure. Currently, monitoring techniques like ground penetrating radar or GPR are primarily reactive as we find the damage only after the ground has collapsed. My research addresses the urgent need for a proactive data-driven system to predict this risk before they endanger public safety. The aim of this study is to implement a machine learning method to predict ground subsidence risks around water pipelines. Specifically, I aim to compare the capabilities of two machine learning models, which is convolutional neural network (CNN) and random forest model in predicting risk from GPR data. And secondly, to generate automated output that classify subsurface condition into low, medium and high risk categories using real radiogram data. To achieve these objectives, my methodology was structured into 4 distinct phases. First, project planning. Second phase is data collection. Third phase are for pre-processing and modeling. And finally, the last phase is for model comparison and risk classification. In phase 1, the foundation of the study was laid through a comprehensive literature review and problem identification. I selected Perlis, Malaysia as the study area due to its history of subsidence incidents and the presence of critical underground water pipeline networks. During this phase, criteria determination was finalized, identifying ReflectW software for geophysical signal processing and Orange data mining software as the implementation environment for our machine learning frameworks. Phase 2 involved building a robust dataset. I integrated primary data collected from field GPR surveys near water pipelines with secondary data. The secondary data was generated using GPR sync software to create synthetic radiograms, and this simulation allowed the models to learn from a wider variety of subsurface conditions such as specific void geometrics, which are often difficult to capture through field survey. In phase 3, the raw radiograms underwent systematic refinement using ReflectW software. I applied time zero correction, DWOW and bandpass filtering, and background removal to ensure high signal quality for feature extraction. Once processed, the data was brought into the Orange data mining platform. Here, I implemented 2 distinct machine learning framework, which is convolutional neural network (CNN), chosen for its superior spatial pattern recognition, and random forest, utilized for its interpretability and ability to handle structured GPR features. The final phase of this research focused on evaluating the performance of the machine learning models and generating the predictive results. First, I conducted a comparative analysis between the neural network and random forest frameworks. I used standard statistical metrics to measure their reliability and determine which model was most effective at identifying patterns in the GPR data. Once the fittest model was identified, it was used for the automated classification of subsurface conditions, and this process involved sorting the entire dataset into 3 categories: low, medium, and high risk. To interpret these results, I performed a distribution analysis using frequency charts and statistical curves to visualize how this risk was spread across the study area. The primary outcome of Objective 1 of my research was the performance evaluation of my machine learning frameworks. As shown in the table, the neural network, which utilized a CNN architecture, clearly emerged as the fittest classifier for the Perlis dataset. It significantly outperformed random forest across all metrics, achieving a classification accuracy of 73.6%. More importantly, its area under the curve of 0.883 demonstrates a robust ability to separate stable ground from critical risk zones. The high correlation coefficient of 0.601 further validates that the neural network framework is a reliable engine for automating the detection of subsurface voids that lead to ground subsidence incident. To visualize the application of this model, I analyzed the frequency distribution of the results. This graph confirms that high-risk areas, which label as the blue color, tend to have larger and more complex file sizes, with an average of size approximately 28,712 bytes, while lower risks are smaller in value. The medium risks are labeled with the color green and the low risk is labeled with the red color. And the smooth bell curves show that the results are consistent across the whole dataset, proving that the neural network framework is a reliable tool for finding ground subsidence risk in Perlis. In conclusion, this research successfully demonstrated that machine learning frameworks can transition ground subsidence monitoring from a reactive approach where damage is only identified after a collapse to a proactive system that predicts risk prior to surface failure. My evaluation identifies that the neural network CNN model as the study's fittest classifier. It significantly outperformed the random forest model by achieving a 73.6% classification accuracy and a robust 0.883 area under the curve. This provides utility managers and urban planners with a vital decision support system to prioritize maintenance in critical zones. To improve the impact of this study, future research should expand the predictive framework beyond water pipelines to include gas and sewerage networks, creating a comprehensive multi-utility risk assessment system. It is also recommended to integrate real-time environmental data such as rainfall intensity and groundwater fluctuations to enhance the model's predictive precision during significant weather events. That's all from me. Thank you.